Thus far, we have looked at the data that we're using in Chapter 3, we cleaned it, and we examined the relationship between our different predictor variables and the outcome variable, which is the response to that term deposit offer. We also created our kitchen sink model, ran it, and then used stepwise regression to determine our parsimonious model. And we trained and created that parsimonious model using our training sample. So now we want to see how well that model is actually doing on predicting outcomes in our test sample. So we can approach this the same way we did in Chapter 2, which is we'll create a density lattice plot, determine a cutoff value above which predicted probabilities are coded as 1 or yes, and below which predicted probabilities are coded as 0 or no. And then we can look at the Cohen's kappa and predictive accuracy to determine the performance of this parsimonious model in our test sample. So to do this, we're going to run the same code that we saw in Chapter 2. We created those predicted probabilities, and then we plot them in our density lattice plot. That plot is pasted into our notes, and what we see is that the curves kind of look similar among people who actually said yes and people who actually said no. So it's kind of hard to draw a line that is going to be a good cutoff. And remember, a good cutoff would be that most of this top graph would fall to the right of that line, and most of this bottom graph would fall to the left of that line. So I don't know, it's just tough because both these graphs kind of peak around the same place and look kind of similar. So that's kind of an indication that our model isn't doing the best job. Let's maybe go with a sort of intuitive cutoff of 50%. So like if the model predicts 51% likelihood of saying yes, they'd be coded as a yes. So we'll run that same code we're used to from Chapter 2. And here you can see we're using a cutoff value of 0.5. But when I run that and I look at our confusion matrix, what we see is that our model will actually predict that nobody says yes. And that's what we also have in our notes. So with a cutoff of 50%, our model predicts 0 yeses. And given that we want to target people who will say yes, and there are actually people who did say yes, this is not a very good cutoff, even though the predictive accuracy of this model is actually quite high. And this cutoff is actually quite high. We can compute that. And we see the predictive accuracy is 91%, but that's because so many people say no. So if you say, yeah, everyone says no, given that such a high percent of people say no, it is an accurate model, but it's not a very useful model because we want to actually be able to predict who will say yes, and this model isn't doing that at all. So maybe let's use a different cutoff value that's a little lower, perhaps 10%. So that's what we have in the second predictive response line here. We can run that and look at our confusion matrix. So here we see that using the cutoff value of just 10% definitely is yielding some predicted yeses. Clearly, a lot of them aren't right. So we see 380 people our model predicts said yes, but actually said no. But 47 are right. So, you know, it's not great, but it's doing okay. We can evaluate it with the predictive accuracy, which is only 63%. We can look at the Cohen's kappa is actually only 0.05, which is a weak agreement. So clearly the cutoff value that we select heavily influences Cohen's kappa and predictive accuracy, and so these numbers can be quite subjective. Therefore, we have another validation tool called the ROC curve, which does not rely on a cutoff value to determine the true predictive abilities of your model. So we're looking at a new validation test, the ROC curve, or the receiver operating characteristic curve, but everyone calls it the ROC curve. So this validation technique does not rely on a predetermined cutoff, and it's the preferred index of performance or validation for low base rate problems. So like what we're looking at, where less than 10% of people are saying yes to our outcome of interest. So this is a low base rate problem. And so the ROC curve plots the true positive rate against the false positive rate relative to if we just had a coin flip model, essentially. So we use the ROCR package we installed at the beginning of the code. Here's all the code. I tried to highlight in red the lines or the variables that you would change if you were to do an ROC curve on a new data set. So all the things I put in red are specific to this data. So bank.model.fit.new is our parsimonious model in this data, in this chapter. Bank.train.sample is the training sample for this data. Bank.v2.df $response is the outcome variable response in our data frame bank.v2.df. So if you are creating an ROC curve in the future, just be sure to change especially these specific variables that are highlighted in red. So we can run this in R. Plot ROC curve. It's kind of a lot of code just to make a graph. What you find is these two curves. So the blue line is the ROC curve for our training sample. So what we use to train and create our model. And then the ROC curve for the test sample is in the red dotted line. And so what you want to see is a curve that gets close to being up in this top left corner, or basically as far away from the diagonal as you can be, because the diagonal represents essentially a coin flip. So what we see here is that the area under the curve is always going to be between 0.5 and 1. So 1 would be if it's basically hitting this top corner. 0.5 would be if you're on that diagonal line and doing equal to chance. So what we see here is that the area under the curve, or the AUC for our ROC curves, is above 0.5. So our model does better than chance, but it could be closer to 1. So I would evaluate, being in this 0.58 to 0.66 range as being okay, but it could be better. A good rule of thumb is that a good AUC is above 0.7 and a great AUC is above 0.8. So if you have an AUC that's in the 0.7, 0.75, 0.8, 0.85 range, that means your model is doing quite a good job. If you're under 0.7, your model is not doing that well. So clearly our model could be better, but we're working with the variables we have and it's the best we can do. So in sum, the ROC curve is not tied to a cutoff value. So we don't need that to determine a cutoff value ourselves or use that density lattice plot to create this ROC curve. And this is the best validation test because it's not dependent on that subjective number from the cutoff value. And it also performs especially well for cases where we have a low overall base rate of response, like when you're reaching out and cold calling clients about signing up for a term deposit with your bank. So the ROC is kind of the rule of thumb and a really, really great tool to evaluate the performance and validation of your model. So now we're finally going to talk about the subject of chapter 3, which is targeting customers. So this study is typical of target marketing. The response rates are low, such that that 50% cutoff we just talked about is performing poorly. In fact, if the analysts used a 50% cutoff, they would predict that every customer would say no, and then the bank wouldn't have any customers to target. Put differently, too high of a cutoff means the bank misses potential sales, but too low of a cutoff means the bank pursues sales of a large number of customers, many of whom will never subscribe to the term deposit offer. So we should choose a cutoff that maximizes profit given the unit revenues and costs associated with each cell of the confusion matrix. Target marketing employed in the right setting and with the right cutoff should yield higher profits for the company. So basically, targeting allows us to be more efficient, and we have a limited marketing budget, and by targeting customers who we expect to be most likely to say yes, it helps us use our money in the most effective way. We're going to cover 2 methods to help determine the optimal number of customers to target. Both methods are using this selected model, the parsimonious model, to select which customers are likely to respond to the targeting strategy. So targeting strategies include things like cold calls, promotional offers, emails, etc. So the first thing we're going to examine is called a lift chart. So the analyst sets a cutoff probability value, and this value affects the financial performance of the targeting model. One approach to selecting the right cutoff value is to compute the lift, or the response rate the predictive model obtains over and above the response rate observed in the entire customer base, so above the average. Essentially, you want to be targeting people who are more likely than the average person to say yes. That means you're being more efficient with your money than if you just randomly drew somebody, and that person would probably be average. Therefore, this lift chart orders the customers by their predicted probabilities of responding to the offer and computes by how much this predicted probability is greater than the base rate of responding to the offer, that average amount. So the lift is the ratio of predicted probability of responding to an offer and the base probability of responding to an offer. So you are looking for a lift above 1, because if the lift ratio is 1, that means the predicted probability of responding is equal to the average or the base probability of responding. And so that's just the average person, and your model is not helping you anymore. So by looking at a lift chart, you can select that proportion of consumers who are more likely than average or have a lift ratio above 1. So the base rate response, the baseline response rate equals the proportion of the test sample who responded affirmatively to the offer out of everybody. So that average response rate. So we can calculate this just kind of raw in our data. So we see that the base rate is 0.08. That means that 8.31% of people said yes. So basically the average person is, in our data, is 8% likely to say yes. So to be most effective and efficient with our targeting marketing budget, we should only target and reach out to people who are, our model predicts, are more than 8% likely to say yes. Otherwise, we're targeting people who are below average, and that's kind of a waste of money because they're less likely than the average person to say yes. So to help us do this, our lift chart orders people from most likely as predicted by our model to least likely. And so then we're able to kind of slice and pick a spot where everyone is more likely than average to say yes or less likely than average to say yes. So to do that, we're again using that ROCR package. I put the code in our notes. So it's also in our R code. So you're just going to highlight and run everything under that lift chart. And what we get is a chart like this, which I believe is also in our notes. Yes. Please scroll down a bit. You also see it in your notes. And so basically we see on our x-axis the proportion of clients from most likely to subscribe, so that's closest to 0, all the way down to least likely to subscribe, down by 1. And then we have on our y-axis the lift over the baseline. So our baseline was that 8% likely to say yes. So you can see this blue line is way higher than that baseline. So the red line represents that baseline, and the blue line is much higher than average. So it's all the way up here. So you basically want to target customers until they reach average. So until the blue line intersects the red line. Sometimes the lift chart is a little messy and it might cross it a few times, like you see around 0.6 here. But I would say maybe targeting the first 40%, 45% would be appropriate. So this lift chart is a really easy visual tool that allows you to see the average response rate in your sample, so that red line, the predicted likelihood of response rate in all of your data, which is that blue line, and then it then shows you when those intersect approximately what proportion you should actually target with your strategy. You can also just simply print the deciles, so those groups of 10% of clients or customers in your data. And so it just kind of gives you some cutoffs that numerically you can see and visualize who you should target. So you can see in decile 1, the average lift is 1.47. So that means their average person in the first top 10% in this graph is 1.47 times more likely to say yes than the average person in the whole sample. So remember, the average was about 8% likely to say yes. 8 times 1.47 is about 12%. So the people in the top 10%, based on our model, are about 12% likely to say yes. And so you should target them, because even though 12% is a low number, that's about 1.5 times higher than the average person. So that's good. So basically you want to target until you reach around 1. So the first decile is above 1, so that's good. The second decile is above 1, you should target them as well. The third decile is above 1, you should target them. The fourth decile is above 1, but then around the fifth decile, we dip below 1. So it's not a good one to target. For some reason, it kind of goes back up for the seventh decile, but because we already crossed 1 and got into under 1 for the fifth decile, I would recommend stopping around the fourth decile. And so this decile, remember, means 10%. So this would be the top 40% most likely to say yes, according to our model. And that's visually represented as well in that lift chart. So these are, both of these numbers and graphs are giving you the same information, that you should target the top 40%, or that 4.4 proportion of clients as estimated by the model, because they are as or more likely to say yes than the average person in the entire data set. Just as a practical matter, though, you should remember that most direct marketers have a fixed budget and they can only mail so deep. So this is kind of answering the question of, well, why not just reach out to everybody? Even the least likely person has some chance of saying yes. The answer is because time is money, and calling customers takes time and money and effort, and it's not always worth it. So you have to decide who to spend your budget on, because that budget is fixed. And so this suggests the top 40%, the top 4 deciles is appropriate in this data set. In some cases, your company might only have money to target the first 10% or the top 1 decile or 2 deciles. And so that makes these lift charts and the deciles even more informative, because you have to really decide where to draw the line based on your budget. So to help evaluate a cutoff like this top 40% we've been talking about, the top 4 deciles, you can use tools called the sensitivity and the specificity. So we can look at, once we pick a proportion to target and we actually implement our targeting marketing, we can look at the sensitivity and specificity of the results. So the sensitivity is the proportions of ones that are yeses that are correctly identified, which is known as the true positive rate. Specificity is the proportion of zeros or no's that are correctly identified, which is also known as the true negative rate. So let's imagine we have 100 customers, and in actuality, 50% will respond to a marketing promotion and 50% will say no. But we don't know these rates. We just have a model and estimates. How should we target our customers depends on the cost of doing so. So basically, how deeply we should target depends on our model and how much money we have. So let's imagine case 1, which is that we care about reaching as many customers as we can. So we decide to target 90% of customers. That means our cutoff that we used was the top 9 deciles, or the 90% of clients. Then we could see our model predicted those top 90 people who would say yes. So that would be this yes column. And then we actually see how many said yes. Only 50% said yes. So only 50 people said yes and 50 people said no, but we reached out to 90 people. And we did not reach out to, we did not reach out to 10 people. So we want to evaluate the effectiveness of this campaign. So this strategy of targeting a huge proportion, 90%, is a great strategy if we are trying to target customers with a relatively cheap promotion. Maybe it only costs 5 cents to send an email and we expect a huge profit margin per customer. In this case, sensitivity is far more important than specificity. So we want to have a situation in which the sensitivity percentage is higher than the specificity percentage. So you can calculate the sensitivity. So that's the number of true positives. So that yellow box where we predict a yes and it's actually a yes, divided by all positives. So that would be those that we actually predicted would be a yes and those that we predicted incorrectly. We thought would be a no, but were actually a yes. So the yellow box divided by the yellow box plus the green box is 96%. This means that 96% of all of the people who actually said yes were actually targeted and reached by our promotion. We can also look at the specificity. So that is the number of true negatives divided by all negatives. So that would be that blue box divided by the blue box plus the purple box. So we predicted no, and we actually was a no, divided by all actual no's. Well, we get a 16%. So that means we have correctly identified 16% of all failures. Conversely, we spent time and money targeting 84% of people who ultimately did not buy. So we kind of wasted time and money on 84% of the no's. So in this case, we see the sensitivity percentage is 96% and the specificity percentage is 16%. And that's the kind of, the fact that the sensitivity number is above the specificity number suggests that this is a good strategy if we have a cheap promotion, because we are reaching lots of people and a lot of them who we reach out to say no, but that's okay. Let's imagine a different case in which we really care about maximizing effectiveness and not wasting money. So if we do that, you're only going to target a small proportion of your customers. So maybe the top 20% of our customers based on our model. So you can see that here, we only target 20 people. That's why there's only 20 in this yes column. Ultimately, 17 of them said yes, and they took on the promotion, and 3 of them said no. So this is a great strategy if the promotion is really costly. So maybe mailing a catalog is obviously more costly than sending an email. So we want to really make sure we only reach out to and do the promotion for people we're pretty sure will say yes, because we want to minimize wasting money on people who ultimately say no. So if this is the case, we want to maximize specificity. So we can calculate sensitivity and specificity again. And what we find is that the sensitivity of this campaign is 34% and the specificity is 94%. That means that we spent time and money targeting only 6% of the people who ultimately did not buy. So this is, a sign that because this was quite expensive, it was appropriate for us to maximize specificity. So it's good that specificity was larger than sensitivity. So in sum, we should, to kind of like summarize what we see in these two cases. In case 1, we spent money and time promoting to 42 people who did not become customers. And in case 2, we spent time and money promoting to just 3 people who did not become customers. In case 1, it was just emails. So it was really not expensive to target those 42 people who did not buy. But in case 2, if we were mailing out catalogs that were expensive to ship, it's kind of a big deal if we had 42 people who got that expensive promotion and then didn't buy from us. And so that's why we, in case 2, you target to a smaller proportion of customers and you really want specificity to be higher than sensitivity. So in sum, you should maximize sensitivity for cheaper promotions and maximize specificity when the promotion is expensive. On a quiz, you might need to apply these numbers by, if I gave you these types of tables, you'd have to maybe calculate sensitivity or specificity, or tell me if I gave you tables, which is probably higher, or which strategy would be better if you care about, or you're using a cheaper promotion versus a more expensive promotion, which strategy would be more appropriate, and would you be maximizing sensitivity or specificity? So those are the types of questions I might ask on a quiz. This seems like the only real calculation or math that might be involved, and it's just a simple division. So I think this will be more straightforward than, for example, chapter 1 was. I believe that summarizes chapter 3. So thanks for watching.